Hi, Year 11. So we continue in chapter 15. 15G is about polar coordinates and the conversions in between Cartesian coordinates, and 15H will look at how to graph using polar coordinates or polar functions. Alright, first what we look is a point P on a curve on the Cartesian plane can be described using Cartesian coordinates. Instead, what we're going to use is a new concept, which is polar coordinates. So instead of describing its x and y coordinates, what we do is r is the radius, which is the distance from the origin, and theta is the angle from that straight line compared to the positive x-axis. So using the properties in the right angle triangle, the x and y coordinates can be written as expression of polar coordinates as followed, and vice versa. If you wanted to go the other way around, you can express your radius in terms of x squared plus y squared as a square root, which is the Pythagoras theorem. And using your trigonometric ratio, the main one we can use is tangent, which is your opposite over your adjacent, or your y over x. There is a pattern on polar coordinates. As your angle is, you will add a full revolution or a multiple of it, which is 2 pi. Then you will end up with the same point. So you can have your angle being a formula when you add or subtract a multiple of 2 pi. If instead you add a multiple of 2 pi plus an extra pi, what you end up is you add half a revolution, and as you the point is moving on the opposite direction of p, which is your p prime here, that argument has an extra pi, but what you end up is also having a negative radius. Okay, so if you end up with having a negative radius and add an odd multiple, then you end up still going back to this point. Okay. Alright, to convert polar coordinates into Cartesian coordinates, you need to know your exact values in the first quadrant for your trigonometric ratios, mainly cos and sine, and also use the symmetry between all the quadrants to determine the actual values. As for example, this situation 5 pi on 6 is actually in the second quadrant. So you will do your substitution and simplify your ratios using your symmetry and knowing your exact values, and you end up with the Cartesian coordinates. Here you will need to pause the video and determine those from the ratios. It's for you to practice your exact values. Probably check it in the answers in the book, or you can use your CAS calculator as well. Okay. All right. What? Okay. Now for you to practice, you have Cartesian coordinates, and you need to turn them into polar coordinates with two writings, one with a positive r and another one with a negative r. So you use your expressions, you find your radius and your angle. That gives you your first set of polar coordinates, and to get the second set, you turn your r into a negative, and for your angle you just add or minus pi. Okay, and you end up with your new angle. So those are equivalent points, they are the same on your Cartesian plane. And you would do the same for b. So I would pause the video and attempt this one. So again, using your formulas, you get using the same process. Pause again the video and attempt C and D. And here are the answers. So just check your answers, have a look at the working out. It's the same process as what I described in example A. Alright, now with the graphs using polar coordinates. So in polar coordinates, what you do is you will have a function, is r will be the subject and it will be a function of the angle. And r and theta will describe the polar coordinates. We can use polar coordinates to describe an example, a circle centered at the origin of the radius a. A is being fixed, so r equals a. And what you do is, because theta is undefined, it means theta is now a variable. It can be any angle, so you're describing the position of a point on a circle. You can do the same with a straight line. Instead of having, now your radius is variable, but your angle is fixed to a value of alpha, and that they will describe a straight line. And if you need to do the conversion between the two, you need to remember those expressions or formula. To sketch the spiral of a polar equation, so you have that polar equation, your theta is varying from 0 to 2 pi. What you need to do is use main points, so you have theta equals 0, pi on 2, pi, 3 pi on 2, and 2 pi. You substitute into r and you place them on your Cartesian plane, and then you join it smoothly. That's how you end up with that Snell spiral. Notice the start and end point as your angle is starting and finishing at those values. Here a little bit of algebraic manipulation. You have your polar equation. The trick here is you multiply both sides by r to reveal a r sine theta on the right hand side, which gives you your y. To get your r squared, you know from Pythagoras theorem, r squared is equal to x squared plus y squared. You substitute into your polar equation, so now you end up with an equation that only has Cartesian coordinates. Then you regroup on the same side, complete the square. That's the new strategy you have to consider at times for a circle and ellipse or hyperbola equation, and that gives you your equation of a circle. The center will be 0, 1, and the radius is square root of 1, which is 1. A little bit of conversion between the two. So B is the opposite of A. For A, you use the expression formula of x and y. You will use the same for part B. You substitute x and y into your equation. You end up with the polar equation with only r and theta. Make r the subject, and this is your final polar equation. With part B, you use your x and y formula, but you make cos and sine the subject. So you end up with x over r and y over r respectively. You substitute into your equation and you rearrange it, manipulate it until you don't have any fractions, and that gives you this equation, which is a straight line. And that's it for today. See you later.